Hello, in this video we are going to discuss about the stability and the closure of orbit under the central force. Now, an orbit that we have come across while discussing the gravitational forces, the potentials involved, the stability term is usually associated with the potential. Now, the potential energy when lies at a very lower value, a system is stable only then. That means that the lowest value of potential is where the system wants itself to be in order to be in a stable, in order to achieve that stable state. We have observed this case in many aspects, many dimensions that we have studied, be it the case of electrons orbiting around the nucleus, be it the case of the as I'm going to state over here, the planetary motions involved. We have been discussing about the central force and the objects which are involved, the two body central forces, where one of the objects, if the mass is greater, while is much greater than the other one, so the second mass is usually considered to revolve about the former, and then the orbit along which it revolves is stable and can be said to be closed as in the case where it comes back to its initial point after a certain time. Just like the planetary motion, as I mentioned, the earth revolving around the sun takes 365 days entirely to come back to its original position or initial position, thereby completing its revolution around the sun. And it's a closed orbit, it's not an open orbit. Had the orbit been an open or not closed, then it wouldn't have returned to its initial position. So these are some of the things and the related conditions that we can have for these topics that we are going to discuss is what we have at hand right now. So if we are considering the energy, let me use another ink for you. If we are considering the energy, now this is the total energy and it comprises of the uh, kinetic term and the potential term. The potential term, however, can be further, this is the pure potential energy that we have, the last term, and this second term that we have mentioned, this can be taken as the centrifugal term, because we are taking the total uh, term over here that I have marked as the effective potential. We are taking it as the effective potential, which is a combination of two factors, which is the actual potential that we have plus the centrifugal potential term. This is the centrifugal potential term, and as we know, this is also equal to mr square theta dot square. Now the whole idea of it is to get rid of that theta if possible, and we are restricting it to a single dimension of the radial component, that is. So we have the value of E now, which can be expressed as r dot squared UE r. Now as we know that the acceleration of the system, which is the net force that is acting on the system, is the radial force and the centripetal force that we have, and the potential the pure potential, that is the regular potential that we have, which is the first term over here that we have written, is of the form of k by r, which means it is negative. It's negative because the masses that are involved, the gravitational force does the work all by itself, and that is why it's negative. Now, at the extreme points, if we consider now extreme points where, well, we may consider the motion and the motion where the distance r, that is between those objects. If you remember, we had considered the diagram where we had the massive object and the lesser mass object, which comprise the two body uh, system, and we had a center of mass mostly in these systems where the smaller mass is much less than that of the bigger one. The center of mass usually lies within the bigger mass, but we are not really concerned about the center of mass because we have now considered the bigger mass as the origin of the system, while the smaller mass revolves around it. So that is the radial distance that we see, that is r. And we now consider the variation of the potential energy term with respect to that radial distance, and we obtain the case where the potential energy is the least, which is what it will favor in order to remain stable. Now, if we were to consider the variation of the potential with respect to the radial distance, then as we can see, the effective potential that we have given over there, that is this is the effective potential term, and that consists of two terms, one being the usual potential energy, and the other being the centrifugal. Now, the potential energy, as we have seen, is this. It's varying as the inverse of r, while the centrifugal term is varying as the inverse of r squared. Here, the variation is in negative terms. So if we plot them individually, then we have their nature something like this. The centrifugal term will move in this way, and finally it will be asymptotic. Obviously it will meet the radial axis at infinity, and the other term, that is this is the centrifugal term, so this is UCF, which is obviously related to r. And then we have the other term, which is the regular UR term, and it is varying negatively, and so we have it along the negative axis, and it's also asymptotic in nature. It will also go to 0 for r going to 0. So this is how the variation is actually not that pronounced. Let me just rectify that. It's something like this, because it's not really that pronounced, because it's going to vary. It's just the inverse of r in the negative coordinate, while the other one is more pronounced because it is r squared, inverse of r squared. So that has to be more pronounced. So this is the UR term, and we have the UCF term, and the effective potential is obviously a combination of both of these, and which will have a greater impact. Obviously UR, which is simply the inverse of R, which is varying as inverse of R, will have a greater impact, considering that as the value of R increases, or if the value of R is even less, it's just in the negative -1 power, whereas the other term is in the power of -2. So that will change immediately or vary immediately, and with any given value of R. For higher values of R, it will approach 0 at a greater rate as opposed to the case of the general potential UR. So the resultant of these two will be somewhat like this, where UR is having a greater uh, strength as opposed to UCF, and that is why the graph remains in that lower region mostly. It starts off over here at lower values of R, and it ends along this direction. Now this is the point where we are going to get the value to be 0, not 0, we are going to get the value to be the least for that potential, and let that distance be r0, which is the ideal distance, so that this thing, or this uh, orbital motion that we say, we haven't proved it to be an orbit yet, because we haven't obtained the closure relation, and we are just saying that stability of that position or of that motion is valid at that particular point, which is r0. Anywhere close, anywhere less than that or anywhere greater than that won't really have, or won't really lead to a stable orbit. So what we do is we just try to find out what this distance r naught is. We consider a mathematical approach to obtain that value of r naught, and from that we can obtain, or we can have the conditions. So let us say that we have the variation of the potential as this, that is, the UR term is equal to supposedly a r to the power n plus 1. We could have taken it to be a r to the power n, but this will help us in the calculation, so it's better to take it as a r to the power n plus 1. And then we know that the centripetal force term for the potential energy is going to be of the order of r to the power -2. So there's no problems with that. Now with these two available to us, we have U effective to be equal to the sum of both of them, that is a r to the power n plus 1 plus b r to the power -2. Now let me erase that, it has overlapped. Alright, looks better. Now in order to obtain the minima, the process that we follow is take the first derivative, equate it to 0, and then obtain the value of r for that derivative, for that after equating it to 0, and then we place that value after we have taken the second derivative. That is how we obtain the minima. And the minimum condition is that the second derivative term after using that value of r that we have obtained from the first derivative must be greater than 0, which is to say that first we equate due by dr to 0, and then we take that value from this to be r naught supposedly, which is the value of r in that case, and we take the double derivative then, and from that double derivative we apply r is equal to r naught, and we have the value. And this value that we get must be a positive one, that is must be greater than 0, so that this orbit firstly is stable and in that r0, as well as it has a minimum value. Now if this d2r by dr square is negative, comes out to be negative after using that value of r naught that we have obtained, then it will be the condition for maximum, and maximum potential is something we don't want. We want the minimum potential or the minimum value of potential, so that the orbit or the motion involved is stable. So this is what we need to do, and let's check it for ourselves. For what value of r naught are we going to get this? Now we have already chosen the effective potential. Now remember one thing, that what we do here is that in this case where we are taking the effective potential and those extreme points that we will be obtaining, that is whether the maximum or the minimum, the extremum, the kinetic energy term is obviously going to be 0, because as you know, let's assume the case of a pendulum. The pendulum at extreme points doesn't contain the kinetic energy term, so the energy there is simply equal to the potential energy, which is the maximum value of energy. So at extreme points that we can have, if we take this graphical interpretation that we have with us, the extreme points that we can have, that is for a minimum value of r and for a maximum value of r, the energy is completely equal to the potential energy term. Now so we are to take the derivative, so we'll be doing that. So taking the first derivative of this term that we have at hand with us, we get due by dr to be equal to 0, which is equal to n plus 1 ar to the power n, and then minus 2 b r to the power minus 3. And from this we have the value of r naught. Now before jumping over to the value of r naught, it'll be easier for us to deal with it like this, that we take this value, we take it to the other side, of course, n plus 1 a r to the power, if that is taken to the other side, is we leave it as r to the power n, we take that as positive, while the negative term is taken to the other side, we get it as 2b r to the power minus 3. Now r to the power n can go to the other side, and what we have is n plus 1 a is equal to 2b r to the power minus of n plus 3. We have taken the minus out, and we have minus of n plus 3. And from that we can have r to the power minus of n plus 3 to be equal to n plus 1 times of a divided by 2b. Now, the reason I do that because it'll be easier for us to determine those values that we are supposed to. Now this is the value of, this is r naught. Okay, we are taking it as r naught. After equating it to 0, we are taking the value of r to be r naught. And carrying it out on the other side over here, there is now we will take the second derivative of this term. The second derivative for that will be d2 ue of r divided by dr squared, and that is going to be equal to n times of n plus 1 a r to the power n minus 1 plus the second term, minus 3 gets multiplied, and so we have plus 6 over here, b r to the power minus 4. Now we will be applying the value of r naught instead of r over here, the r naught that we have obtained. But we remember we have obtained the value of r naught in the power of minus whole of n plus 3. So what do we do? Well, I'm just taking it as r equals r naught. So these terms are simply r naught instead of r. What I can do is that I can multiply this entire thing by r naught to the power 4. So let me do that. If I multiply that entire thing with r naught to the power 4, but I cannot just do that all according to my whims and fancies. If I'm multiplying them, I must divide the entire term by r naught to the power 4 as well, so that it's nothing like it has come out of thin air. Now with r naught to the power 4 multiplied at the top, what we end up with is that as it goes in and gets multiplied to the first term, we end up with r naught to the power n plus 1 multiplied with r naught to the power 4, which means r naught to the power n minus 1 plus 4 is going to give me r naught to the power n plus 3, isn't it? So the first term that we get is n times of n plus 1, and we have a r naught to the power n plus 3. Now, and as for the second term, we have r naught to the power 0 left, so we are only left with 6b, and this entire thing now is multiplied to r naught to the power minus 4 that was there in the denominator. That has come up, and we have the negative power of it. So this is what we have, and if you observe, r naught to the power minus of n plus 3 is this is just the reciprocal of that. So that means this value is the reciprocal of this right hand side value, which is 2b divided by n plus 1 times of a. So let's do that, but we'll be doing that in the next page. So let's refer that thing, n times of n plus 1 a, n times of n plus 1 times of a, and we have r naught to the power n plus 3, which means is equal to, that we see on the right hand side, 2b divided by n plus 1a. 2b divided by n plus 1a. And then we have the 6b term. So plus 6b, and this entire thing multiplied with r naught to the power minus 4. What is this? This is obviously d2ue divided by dr squared. And this n plus 1a can cancel out. We have 2b taken as common term, and that multiplied with n plus 3, because this is going to give me a 3 after I have taken out 2b from that, and r naught to the power minus 4. So this is what we end up with. Now this term, obviously b is a constant, positive constant that we have considered, and r naught is positive, the value is changing, positive value, but the thing that it will be positive only when we have n plus 3 to be greater than 0, or we have n to be greater than minus 3. So that is the condition we are getting for stability. And from the values that we have observed, we come up with two such values which will be proper to describe this. We have n to be equal to minus 2, which is obviously greater than minus 3, and we have the value of n to be equal to 1, greater than minus 3, of course. For those two values of n, we have the value of potential, which was, remember, the potential term, plane potential, that is, the centrifugal potential is varying as r to the power minus 2, so that's not a problem, that is fixed. But what about this term? This is what determines the potential energy of the system. So the potential that we had is equal to a r to the power n plus 1, if you remember, which is, and if we are to take the derivative of it, then what do we have? And in fact we are taking the negative derivative of it, because that's how the force varies. So force, a conservative force, that is minus dur by dr, and so that is equal to, that is going to give me n plus 1 in the negative, a times of r to the power n, a times of r to the power n, which is of the form minus k r to the power n. K is some constant value. Now for n equals minus 2 that we have taken over here, we have the force to be of the form minus k by r squared, which is the inverse square law. And this follows a closed orbit. And for n is equal to 1, we have, so this is for n is equal to minus 2, and for n is equal to 1, we have Fr to be equal to minus Kr, and if you see, this is the form of Hooke's law. Now both these values of n, they are the values which satisfy the stable and closed orbit condition. There are very different values of n for sure for stability, of course, because anything n greater than -3 is going to give me stable orbit. But here the closed orbits are closed and stable, of course, are under the condition of n is equal to -2 and n is equal to 1 only. And the known or the associated laws that we have related to those values of n are as given over here. So these were some of the conditions that we were supposed to study in this video on the case of central force, and we'll be continuing with some parallel videos as well related to the numericals for better understanding of the topic. And we'll be moving further with the case of the virial theorem as well as the scattering cross section. We also have a separate segment for the satellites. That is all to follow in the upcoming videos. Till then, thank you for watching.